Hello guys, welcome to Insight Electronics and welcome back to the part 2 of the power factor correction series. Now in my previous episode I have demonstrated how a capacitor can be used for correcting the power factor or to improve the power factor, shall I say. So in this episode I'm going to show you the situations where you cannot use a capacitor for the power factor correction, because in my last video I have already mentioned that it is not like you can pick any capacitor, any random capacitor and stick it across the main and expect the power factor to be improved. There are some calculations that has to be done to get the proper value of capacitor. Otherwise, instead of improving the power factor, it's going to worsen the situation. So that is what I'm going to demonstrate in this video. So if you're familiar with the things called energy saver devices or power saver units and things like that, I'll put a picture in the screen right now. Those are basically a capacitor. So the scammers actually make use of a kind of setup that I used in my previous video, and with the help of such a setup, by connecting a capacitor in parallel to the load, they will actually show the current draw being reduced, and they claim it as the energy being saved. And that is what most of the people fall for, because for their eyes it looks like clearly when the capacitor is plugged in or the so-called energy saver is plugged in, the current consumption is actually going down. So yeah, clear winner, right? So it works just because at that particular instant the capacitor is actually tuned for that load that they were using. And when if you have purchased one of them and for the hope of getting an improved power factor, which is not at all required, because for now the domestic users are not being charged for the apparent power. So let's assume that you have purchased one, or you try to make one by yourself by putting a capacitor across the mains, and you are experiencing something really bad because now the load is like acting weirdly. Why is it so? It's because now the random capacitor that you picked is not matching with the load and it's creating an even worse scenario. Let me demonstrate. So right now I have made an unbalanced load or a dummy load by putting an inductor in series with a bulb. So this is actually an RL circuit. So basically an inductive load, but not a pure inductive load like a motor. This has some resistance and some inductance, so like a typical appliance. Alright, so I have connected it to this meter, you can see over here. Now let me plug it in. The fan is now not running at the moment, so let me just plug this in and I will show you the readings. You can see the light bulb is on, but with much less intensity because there is an inductor in series and it's acting like a resistor. The inductive reactance is kicking in, and that's why the bulb is low. And here you will see 227 volts at the moment. The current being drawn is 120 milliamps. Power factor is 0.6, 0.6, that's the worst power factor. And the true power consumption is 18 watts. Alright, so this load has a true power consumption of 18 watts, and let's see what will be the apparent power of this device. Because of such poor power factor, the apparent power will be 18 divided by 0.5, that is around 36 watts. So for the grid, this setup is acting like 36 watt power consuming device. So let's assume that now you have purchased one of these power factor devices, and for the sake of improving the power, you're going to plug it in to the wall, because those things are advertised that you can plug it at any wall socket, just like I did right now. I hope you guys can see that I have plugged it over here. Let me show you. This wire over here, this connector over here, goes straight to the capacitor. Hope everything is in view. Now I'm going to plug it in once again, and you can see the load is on and the capacitor is now in parallel to the load, the whole setup over here. So let's see the readings. 225 volts, 226, there is a little bit of fluctuation going on. The current draw is actually around 600. 0.1, the power factor is 0.1. You have significantly worsened the situation, and 19 watts of power. That's an absolute disappointment right there, because that is what you're actually getting if you're purchasing one of these, and in the hope of improving the power factor when you plug it in across a unmatched load, because you have witnessed by yourself how worse the situation has become. It was actually 0.5, now it has turned to 0.1 because the capacitor is not matched with the load. And this is what happens when you're this is what happens, when you're putting power factor correction units in your home as well. In fact, what is the point in here? Now the power factor is actually 0.1. So what was that? 18 watts divided by 0.1 will be 180. So with the 0.1 power factor, this unit has become the equivalent of 180 watts. You have actually seen the current draw being increased because of this bad power factor. So this is the reason why you cannot put any random capacitor and stick it across the mains to expect to improve the power factor. Let me show you with another load as an example. Just I'm going to plug out this light bulb, and I'll be plugging in a fan, this one over here. This is just a different kind of fan, an AC blower fan in fact. So I'll be connecting it in here, and by the way, this is a series bulb tester. I have made a video about that. I'm going to plug it in, and you can see the fan is spinning over there. Let's take a look at the reading. Now the inductor is in series with the fan, so that means that's the reason why it is spinning at a much lower speed. Now this is actually a pure inductive load right now, because this is an inductor, the fan is a separate inductor, so it's a pure inductive load right now. So 227, 228 volts at the moment, 70 milliamps of current, 0.5 power factor again, and 9 watts. This AC blower fan alone is around 18 watts, and now because of the inductor in series, it's going to act like a resistor, so the power consumption has been reduced. Now I'm going to plug the capacitor to the supply outlet. So now the capacitor has become parallel to the inductor setup, just like we did in the previous setup. So I'm going to power it on again. You can see the readings. The only difference is that now the capacitor is in parallel to the whole load setup. So let's take a look at the readings over here. 229, approaching 230 volts. 0.6 amps. 0.6 amps. Again, you can see the difference. Power factor is 0.07. 0.07. Imagine that. 11 watts. 0.07 power factor. You have made the situation even worse. Let's see what is the actual power consumption. What is that? 7 watts divided by 0.05 or something. Yeah, whatever. 140 watts. So this setup, because of the unmatched capacitor, has become acting like 140 watts of load. And this is the reason why you should not use any random energy saver devices. No matter what the load is, it's going to sometimes it may be good, but it's better to avoid it, because otherwise these kind of things can happen. Now you are unknowingly stressing the load, because now this will be plugged into some wall socket, and this load setup will be in some other room. But then again, when everything becomes parallel, the situation gets worse. So now again, let's continue the experiment. I have disconnected the capacitor, I have bypassed the inductor. Now the fan will be on its own. So if I plug it in, you can see the fan is now in the full speed. The readings, again, the voltage is 230 volts. Normal 110 milliamps of current. That is the actual power consumption of this device. 0.7 factor, 0.7 power factor is, and 20 watts of power. That's what this is actually rated for around 18 watts, but 20 watts well, fine. Now I'm going to connect the capacitor in parallel to this one, because this had a 0.7 power factor. Now the capacitor has become parallel. Again, the inductor is not in circuit, it has been bypassed. So I'm going to plug it back in. Again, 228 volts, 600 milliamps of current, 600 milliamps. The power factor is now down to 0.1, 0.1, 21 watts. So you have witnessed by now that why you should not use any random energy savers, let alone be capacitors or those ready-made energy saver devices in your house at all, because you are unknowingly connecting you are unknowingly making a good power factor to a worse power factor, or you are turning a somewhat okay power factor to a bad power factor. That is the only thing that you are going to do. I agree. So there are some occasions where the whole thing will work, but there is no guarantee that absolutely it will work with every single load. So I hope you have now understood why you should not use power saver devices in your home. And yeah, if you have any doubts, just hit me in the comments below. And so that's it for today's videos, guys. Thanks for watching. See you in another video.